Thank you, Elias. So for a brief overview of what I'm going to be talking to you about today, I'm just going to go through what density and functional theory is and go through the background of it and formulations of density and functional theory, because it's kind of a very large topic and it's much easier if you kind of break it down. Then I'm going to just go to a few concepts that are a bit beyond density functional theory. And then I'm just going to talk about how I use density functional theory in Monte Carlo in my research and go through an overview of diffusion, and then just go through how I use this in my examination of the Wadsley-Roth phases, which are to be used for battery materials. And so density functional theory is a computational tool that's used to examine the electronic and atomic structure of some many-body system. And by a many-body system, I mean something where there's going to be multiple ions and electrons. And it pretty much breaks a very, very large and computationally expensive problem down to a less computationally expensive problem. And the basis of it is that kind of shape it. So the first theorem is the fact that the ground state of a many-body system can be uniquely described by the electron density. And so this doesn't really say like how or like what the electron density should be. It's just that there is one unique solution for the electron density for the ground state. And the second theorem, which states that the electron density that minimizes the total energy is going to be the electron density that corresponds to the exact ground state. So kind of similar concepts. And so the groundwork for density functional theory was, well, first started from the Thomas Fermi model, but there's only so much space on the slide. I'm just going to start with the Schrodinger equation, which was developed in 1926, which, as you'll see, is going to be necessary in order to solve for the energy eigenstates. Then the Hohenberg-Kohn theorems, which were developed in 1964, were what really laid the groundwork for DFT. And then the Kohn-Sham equations are what kind of allowed DFT to be used as a computational tool and allowed for different functions to be produced and allowed for a final computational method. And so for a background for why DFT is useful is that if you have some many-body system and you wanted to solve for the ground state exactly, you would have to use this Hamiltonian, which has terms that correspond to the kinetic energy for atoms, or all the atoms in the system and all the electrons in the system. And then you have these coulombic terms for all the nuclei and all the electrons, and then these coulombic terms that go between the nuclei and electrons. And then you could just apply this Hamiltonian to the wave function that corresponds to the probability distribution of finding a particular nuclei and electron at certain states and solving for the energy. The problem is that if you try to just do this from the get-go, the problem quickly blows up and it becomes extremely computationally expensive, and if you're going to try to do a problem that's like more than a few atoms, you're not going to be able to solve it in any reasonable time frame. So with density functional theory, you kind of break up the problem into solving the energy as a function of this density, or yeah, of this density function. And pretty much you're putting most of your unknown terms into this exchange correlation term. And you don't have to go through all of the different interactions between the electrons, and atoms, and so it just kind of simplifies the problem. And if you pretty much take this this functional, minimize it, and then choose some trial electronic density and trial wave function, and pretty much solve the equation, test to see, and output a new wave function and a new electronic density, and test whether or not the new and the old densities are going to be similar within a threshold. You can pretty much go through and solely try to find out what the actual electronic density that would correspond to this ground state would be.
Muna?
Yeah.
On the last, on that middle cone sham functional, can you describe what the terms sort of represent, what we're accounting for in the total energy?
Yes. And so this term here is kind of a kinetic energy functional. This is a Coulombic term that pretty much talks about the interactions of the different particles in the system. So, well, electrons in the system. So that's what this R and I'm going to be going through. This EXE is an exchange correlation functional. And so it corresponds to the energy contribution from the fact that electrons are fermions. And as fermions, if you take a particle at one position and a particle at a different position and kind of swap them, the sign of the wave function is anti-symmetric. And the fact that, that contribution and the fact that there's kind of like a hole of charge around the electron, kind of like forms like a bit of a hole. There's those different contributions could kind of just be wrapped up into this. And this is kind of the part that makes DFT inaccurate. It's not exactly clear how to specifically represent this. And so you have a bunch of different functionals that I'm going to show later that try to solve for this contribution separately. And this integral is over a external potential that's applied to the system that it kind of just a total external potential that is kind of here.
Sweet, thank you.
And so, as I said before, there's that that functional that corresponds to exchange correlation, and it's kind of unclear how to accurately account for that. And there are multiple methods that are used to try to account for it, but there's kind of a cost associated with having a quite exact exchange in partial correlation functional. And so you kind of have an option of choosing something that's not as accurate, but faster, to functionals that are more accurate, but slower. And these different functionals are more useful for different types of systems. For example, if you have like a metallic system or an insulator. And just a bit of information going beyond DFT, or at least a bit into how these different functionals work, there's the Hearttree approximation and the Hearttree Fox approximation. And pretty much what the Hearttree approximation does is that instead of having just like a total many body wave function that describes all the electrons in the system that are interacting with each other, you split this into all of the single electron wave functions and just multiply them. And so you're not really accounting for all the interactions between the electrons, but it's kind of a good enough approximation, and it kind of gives you a nice starting point that you can either use it in DFT or just separately. And there's also the Hearttree Fox approximation, which actually takes into account the fermionic character of electrons. So kind of that anti-symmetry that I had mentioned before, the fact that if you swap the positions of the electrons, the wave function is going to be it's going to be the negative of the previous wave function. And so you can properly account for that by taking this determinant. Now that I went through a brief overview of DFT and a bit beyond, I'm going to talk about how I use these computational methods in my research. So if I take this really oddly shaped system, so this little schematic is supposed to represent a system or a periodic system of atoms where you have a transition metal in the middle, and then oxygens at this corner, this corner, this corner, this corner, and in the front and the back. And you take this periodic ordering, or this octahedra, and you just kind of tile it throughout the structure, making this weird thing that I'm going to describe in more detail later. And so if I take my base structure and I put lithium at different stable sites in the structure. So this is a particular lithium vacancy ordering where I occupy, in this case, like half of the available lithium sites with lithium. And I can pretty much calculate the energy of this lithium vacancy ordering and other lithium vacancy orderings, and look at what the formation energy is for each of the relevant lithium vacancy orderings and plot it as a function of composition. And so you might notice that there are multiple formation energies for different compositions. If I take this lithium right here and just like pop it right there, that's going to have a different energy. And it might be lower or it might be higher. And these energies that are lowest per composition are pretty much the ground state, or they are the ground state energies. And so they're going to be the lowest energy configuration at that composition. And so I could take this convex hull and calculate the slope of it and get voltage data, and through DFT I could get a variety of different electronic and structural properties. For example, DFT can be used, well, with DFT you're going to be pretty much solving for where the atoms are going to want to go to and where exactly they want to relax to. And so you can see how the volume changes upon inserting lithium, for example, or how the strain, crystallographic strain changes. You can also look at where the electronic charge wants to go in these atoms. For example, you might want to go in this, like near the central transition metal, or to one of these edge transition metals. And a bit more on the voltage calculation. As I stated before, I can use these slopes to find the voltages, and that's because you can use the slopes to find the chemical potentials. the chemical potential at the cathode of an intercalation compound and the anode, and use that to find the actual voltage that you're going to be, well, the DFT approximated voltage. So after I calculate all the different lithium vacancy orderings that I find relevant, and I enumerate a select number of clusters. I'll explain to you what that means in a little bit. I can fit a cluster expansion, which could allow me to predict low energy structures that allow me to calculate lithium vacancy orderings that I think are going to be lower in energy. And so what exactly is a cluster expansion? What are these clusters? Well, a cluster expansion is this complicated equation. It's actually not that complicated. It pretty much states that the energy of a system, if you take this sigma, which is pretty much the site occupancies, so which of these atoms are going to be occupied here, and I take this sigma off to infinity, I could exactly solve for the energy of the system if I knew these ECI, these V naught values, which are called ECI or V alphas. So this cluster or this correlation function right here is going to be a function of the different clusters, or which are pretty much going to be the different points or pairs of points or triplets of points where these points are atoms that you have in the system. So it just pretty much states that it pretty much splits up the energy of the interactions between different sets of sites being occupied versus not being occupied, and breaks it down to this equation. And so if I want to look at all of the unique atomic sites, so if there are like two atoms that are unique in this, or 2 point correlations are unique in this system, then I'd have 2 of these terms where when the point correlation is kind of filled, you would have an ECI that corresponds to that particular point correlation, and you would take this off to larger and larger size clusters. And so when you're fitting a cluster expansion, you're going to be minimizing it. So you could use like linear regression or other regression methods that allow you to solve for what V naught and V alpha would be to the highest accuracy, so the lowest error. After I have my cluster expansion, I could do grand canonical Monte Carlo, which you can see the partition function for it here. It's pretty much a way of probabilistically determining what the most likely states of the different atoms are. So if I had my my little ordering from before, where I have a bunch of different energies for certain orderings that are lower in energy than other orderings, I could say that our grand canonical Monte Carlo would kind of show to what extent I'm going to be sampling those lower energy orderings over the higher energy orderings. And it would pretty much just show me, like, as I go from 0 Kelvin, which is what DFT predicts at, to finite temperatures or high temperatures, what different sites are going to be filled in with what probability. And I can also use this cluster expansion to do kinetic Monte Carlo, which pretty much shows how atoms diffuse in a system. So if I have my little lithium ordering from before, and I want to see, for example, where this lithium wants to go. Like, does it want to go in this direction, or this direction, which is filled, so it can't really go there. It just pretty much shows the probability of it going in or being transported in certain directions.
Muna?
Yeah.
So I have a few just sort of clarifying questions. First, can you explain why DFT is only a 0 Kelvin technique?
So with DFT, you're not using, there's not really any information about how like thermal fluctuations are to be accounted for, I guess.
Okay.
And like you're only dealing with the ground state energies. Like if you're going to finite temperatures, there's going to be a lot of different structures or like orderings that are going to be sampled. And so just having the ground state energy wouldn't be like kind of applicable.
Okay.
So you're not really going to get a ground state until you go to 0 Kelvin, I guess is the correct answer.
And that's really coming out of the Hohenberg, the first Hohenberg cone theorem, right? Like the unique electron density that corresponds to the ground state, right?
Yeah, that ground state is not going to be as relevant if you're not like at, or it's not going to be relevant if you're not at 0 Kelvin. There's going to only be one ground state at 0 Kelvin. Precisely.
Okay.
Mhm.
Okay, cool. On this cluster expansion side of things, cluster expansions still sort of blow my mind quite a bit. So in general, I'd like could you explain like why would I want to do a cluster expansion? If I can do DFT and calculate the energy of a structure and calculate these different orderings, why do I need to do a cluster expansion?
So DFT is a very time-consuming computational tool, even though it's much faster than just going for the many-body problem or like just using the many-body Hamiltonian directly. It still takes anywhere between like 10 to a lot of my systems take like 100 hours. So if you want to get information on a lot of these orderings, then or like trying to predict what some low energy orderings, the cluster expansion would be helpful for that. It's also useful in that the grand canonical Monte Carlo partition function requires an accurate description of the energy as a function of the site correlations. And so you could you need some type of equation that would describe that in order to do grand canonical Monte Carlo, and like to go to finite temperatures and to go to larger and larger supercells. So for example, my grand canonical Monte Carlo simulations are generally done in cells that are about 30 times larger than my DFT cells, because if I tried to do DFT on that, it would not finish in a reasonable time frame. Does that answer your question, or do you have any more?
Yeah. So I think this really gets to the heart of why cluster expansions are important, right? It's really talking about how you can learn from DFT by breaking down some system into these clusters, as you've described, these singlet, doublet, triplet clusters, and then fitting basically the presence of these clusters as a means of predicting the total energy of the structure.
Yeah.
Cool.
In general, DFT is going to be used as a tool for getting training data that you can use for cluster expansion. And
Exactly.
yeah.
Okay, cool. Okay. And then, yeah, I think this is, this, you might already be going over this, but if you could talk about sort of like, if I, and this might be a better thing for the end of the presentation, but just talking about the actual, how do I do a cluster expansion? Like starting out, like where do I start, and what are the important steps that I need to go through to actually develop a model?
Yeah, so I actually don't really have too much on that in this presentation.
Okay. Okay, we can hold that for the end,
yeah.
if that works better then for you.
Okay.
Sweet.
Okay, and I'm just going to go through how grand canonical Monte Carlo works, because I just showed you that partition function, and I didn't really give any more information outside of that. And so if you start with this partition function, and you're kind of at a constant temperature and chemical potential, you can sample what the probability is of being at a particular site occupancy. So pretty much like determining whether or not in the system this site is occupied and this isn't, or like vice versa or something like that. And if you have that, the partition function, you pretty much say this is the probability of this particular microstate or this particular site occupancy where you have a particular ordering, and you divide that by the addition of all of the different orderings that are possible in the system. And after you have that, you can use that probability distribution to get the ensemble average of some thermodynamic variables, like the grand canonical energy, for example. You could also, as I said before, use these computational methods to look at how atoms diffuse through a system. And so there's this particular method called nudge elastic band, which you can pretty much, if you go to the very dilute limit and you make this very, very large like main structure and put a lithium somewhere in it, you could say, you could see what the energy is of putting a lithium, or having lithium go from like here to here, as opposed to here, or something like that. If you do kinetic Monte Carlo, you don't really have to just focus on the dilute limit, or you don't have to just focus on one atom moving. You can look at how multiple atoms move together. For example, in certain systems, the movement of one or two atoms can allow for another set of atoms to move. And the description of these movements can be captured in correlation factors or transport coefficients, where correlation factors kind of show, measure the degree to which hops are correlated. And so pretty much if this is 0, then your atom that hopped here is going to just keep hopping back here and then like back and forth. If this is 1, then your atom that you're kind of tracking is going to be hopping to always new locations, never going back to its previous hop. And so I'm just going to talk about how I use my methods to look, to examine a family of battery chemistries, the Wadsley-Roth phases in particular. I'm assuming that you know how batteries function, so I'm going to just skip this, but state that the C rate of a battery can correspond to how many times you can charge or discharge per hour. Just in case you didn't know that definition, it's going to be relevant in this paper or in this talk. And so why are we looking at the Wadsley-Roth phases? Well, for one thing, they're safer. So with traditional graphite anodes, there's a positive, or lithium dendrites may form on the anode, and these lithium dendrites have the possibility to pierce the membrane that separates the anode from the cathode. And that could lead to runaway reactions that lead to, or that can lead to fires or explosions. And particularly this occurs when graphite is charged at high rates, and it particularly occurs because of the low voltage with which batteries that use graphite cycle at. With the Wadsley-Roth phases, you're using are going to a higher voltage, and so it's safer. In addition, we are looking at the Wadsley-Roth phases because they have a higher power density. Again, if we look at the power density for graphite and the power density for this Wadsley-Roth phase, this NB16W5055 structure, you can see that this power density is much higher for a particular energy density. And so what exactly are these Wadsley-Roth phases? How do you construct them? What does any of this mean? So these Wadsley-Roth phases are going to be constructed by these transition metal O6 octahedra, where again, you have a transition metal in the center and then oxygens at each of these corners. So 6 oxygens around it. And you can take these octahedra and tile them so that there's, in this case, a 3x3 block of these octahedra. And then you kind of form a checkerboard-esque pattern where you take this 3x3 block and then move it out of the screen by a half octahedral unit and then place it. And then you come out with this kind of a full interesting structure. And there are 2 particular motifs that are of interest. One are these vertex sharing octahedra, and 2 are these edge sharing octahedra. And pretty much throughout the presentation, I'm going to be using this type of schematic, and these lighter blue octahedra are going to be at the C=0 level. These lighter ones are half units out of the screen, and these are half unit into the screen. It's just so it becomes clearer. And then I have 3 types of different lithium coordinations. So there's window sites as shown by these lines or diamonds, and these pyramidal sites that are shown by these triangles. And so far, I've found that while examining these structures, there's a huge variety of different Wadsley-Roth phases that are that could be formed. And so I'm going to start with my work on phosphorus sodium oxide. When I started this project, I went ahead and started sticking lithium in a bunch of different places and doing DFT. And by doing that, I found 5 sets of stable lithium sites. So lithium can be in these 3 types of pyramidal sites and these 2 types of window sites. In addition to doing, after I found the different lithium positions, I knew that I could have a variety of different lithium vacancy orderings where you have lithium in some of those stable positions and vacancies in other sets of those stable positions. And what I found after doing a few calculations and doing the cluster expansion method to find low energy ground states was that there is a preponderance of this type of ordering where these window sites are kind of shown in interweaving type fashion. So if I take this as layer 1, this is layer 2, and stack them onto each other, you can see that the window sites are perpendicular to each other. And this can be very important because it shows that there's kind of this particular ordering, which might be important to kinetics down the line. In addition, I did calculations with all of these different orderings, and I found that particular orderings with particular sites are stable at different composition regions. So when I'm at low compositions, pyramidal sites are more stable. At higher compositions, you start to see a mixture of these sites. And this can be important because in a similar system, PINB 207, there was a paper that showed that the fusion mainly occurs in the window sites. And so finding out when that happens or when these are stable can be useful for trying to find out how to increase the rate of performance for these. In addition, I took my cluster expansion and I took all of my training data and I did grand canonical Monte Carlo, and I found this voltage curve. So pretty much I took my cluster expansion and made some gigantic supercell, which was like 30 times the size of my DFT calculated cell. And I sweeped through a bunch of chemical potentials and temperatures so that I could, through a bunch of chemical potentials at 300 Kelvin, and use that to figure out what the voltage would be if I went to 300 Kelvin using my DFT data. And I compared that to experiment and found that it's kind of reasonably good. It's kind of downshifted, which DFT tends to downshift metal oxides, so it makes sense that a method that uses my DFT data as training data is going to also downshift the voltage curve. And we found agreement that at low compositions, the pyramidal sites are going to be filled, and at higher compositions, the window sites will be filled. We also examined the crystallographic strain that occurs in these structures and found that there's only a small volume change that happens when you include more and more lithium, which is what you would want with a battery chemistry or a battery analog chemistry. We also noticed that there's this particular strain that occurs for phosphorus sodium oxide. So it starts out, or we start out the system at low compositions with no strain, and as we increase the amount of lithium in the system, we get to a point where there's a dramatic increase in this crystallographic strain, where you kind of have the block planes kind of contracting, and then there's kind of an increase in the infinite axis. And so it seems that this type of thing occurs in other Wadsley-Roth phases. So it's kind of a neat thing that we found. Also, I decided to look at the charge densities for phosphorus sodium oxide. And I've noticed that at the central niobium sites that electrons are kind of localized in these dxy orbitals, so they can't really bond to anything. They're just kind of hanging out. It's not until we get to higher compositions that we get charge density at on these edge sharing sites. And the charge density here, as you increase composition, allows for kind of metal-metal bonding between these edge sharing sites. And just to be, just for clarification, as you increase the amount of lithium in the system, you're going to be increasing the amount of electrons, because the electron just immediately leaves the lithium and just it coordinates itself to the transition metals or oxygens. I've also been looking at a different system called TINB207, which, although looks similar, is kind of different from phosphorus niobium oxide. And that means that it has different sites that are stable in it. Particularly, it only has two pyramidal site types and two window site types, which is a bit different from the Lazaroff phases. And because of this disorder that you see in the titanium niobium orderings in this system, I thought it would be interesting to see like what titanium niobium orderings would be lowest energy or highest energy. And so I took this structure and I put titanium and niobium in different locations. So some orderings have like niobium here or titanium here, and then etc. And pretty much just went through, enumerated every combination where there is 3 titanium in this 3x3 block and 6 niobium in it. I took those orderings and I did DFT on them and looked at the energies of the different orderings. And I found that there is a kind of theme when we have the titanium at this and this symmetrically equivalent spots, the energy is going to be at its highest. Then if I look at orderings where I have this titanium site filled, the average energy is the next highest. And it's not until we get to orderings where titanium is at this location and this location at the corners that the energy is lowest. And this is important because the local transition metal chemistry affects lithium site stabilities. And the lithium site stabilities are also affect the kinetics in the system. So if you want to make a fast charging Lazaroff phase, it's very important to, or it could be an important contribution. But yeah, I think, what time are we at?
It is 9:45.
Okay, I think I'll just end it early so that there's 15 minutes for questions.
Sweet. Okay. Okay, great. Thank you so much, Muna. Thank you for that wonderful presentation. And yeah, let's open it up to questions. Does anybody have any questions they'd like to ask Muna? Okay. I have one. On Monte Carlos. So Monte Carlos are capable sort of like predicting a structure as a function of temperature, right? How do we really get there with a Monte Carlo simulation?
So with Monte Carlo, you're pretty much going to be, if you know the energy of the structure and you know you apply a chemical potential and temperature, you're going to be getting the probability distribution of certain orderings occurring, because you're going to be looking at how the applied temperature is going to affect the likelihood of getting to higher energy like microstates. So if you remember the different TINB207 orderings that I showed before, and how there were orderings or particular motifs that were filled that caused certain orderings to be higher in energy, right? if you go to higher and higher temperatures, you're going to be able to access those higher energy microstates to a higher probability.
Okay. And so a Monte Carlo simulation, though, is going to basically randomize my structure and then give me an idea of whether or not that structure is plausible, or exactly how is it going to work on that front?
Yeah, so there's a bunch of different algorithms, but if you go through the Metropolis algorithm, you kind of have your, you choose a random microstate, and you determine whether or not changing to this particular microstate is going to lead to an energy penalty or not. And if you lower the energy by going to this particular microstate, you keep the change in going in taking this configuration. But if the change leads to an increase in energy, then you accept with some certain probability.
I see. And that the parameter for which you accept is based on the temperature at which you're running your simulation.
Yes.
Okay. Cool.
Yeah, the probability is going to be dependent on the temperature.
Yes. Yes. Okay, great. Any other questions from anybody in the audience?
I had a question on the first Hohenberg-Kohn theorem. So I remember hearing that that first theorem describes any observable as a unique functional of the density. So other than the ground electronic state, are there any other observables that we're really interested in?
So if you have the ground state, you have like the positionings of all the atoms in the ground state as well. So you don't really only have the energy, you also have all of the different properties of the system when it's at its ground state. So yeah.
Cool.
So yeah. Yes. Anything else?
I'd like to ask just a quick question. If you could just sort of outline again the procedure of if I want to run or if I want to fit a cluster expansion to a certain model system, sort of what are the big steps that I go through?
Right. So the main steps that you'd go through is figuring out all of the symmetrically unique clusters up to some certain cutoff. So let's say, if you were to try to enumerate all clusters in the system, you would go off to infinity because there are infinitely many clusters. This is a periodic system that goes on for forever. But if you choose some kind of distance cutoff and some kind of cutoff of what the size of the cluster you want to, or like you think is going to be relevant, you can enumerate those. You can solve this point correlation function for each of these. And when you have this information, the only kind of unknown is going to be, or the only thing you're going to be minimizing for is going to be these coefficients. So these V alphas are going to be ECI that are specific to all the null cluster. So it's just V0 here, the point cluster, the pair cluster, etc., up to whatever cutoff that you're that you want to go to. So I think, is that clear, or is there still something?
Yeah, I mean, I think that there's this sort of right. You also, like you said in your slide here, you need to enumerate a lot of structures. You need to do DFT, and you need to build the training set data for you to be able to fit that stuff. And then you've created a model that basically lasts a lifetime on that type of system.
Yeah.
Sweet.
Right.
Any other questions? Okay. All right. Thank you so much, Muna. Thank you. We really appreciate you having given this presentation, and a lot of us learned a lot about DFT today. So thank you so much.